on the internets. All right. So we did the birthday thing, right? Remember that?
Yeah.
We had, I can't remember, we had at least one birthday pair in here, right? We didn't have any? Oh, okay, that's right, because there were so few of us. My other class had at least 3 birthday twins. So overall, it averages out. All right. So there's 2 things. First thing is my little brother. He said to me one time, he said, "Do you still teach probability, Jeff?" And I'm like, "Yeah, I do." And he said, "Well, that's shit. It's all shit." I'm like, "Okay, explain." And he said, "Either something's going to happen or it ain't." Everything's 50-50, Jim. I'm like, "Shit, Jim. I'm glad you did not become a doctor." "Doc, what's my chances?" 50-50. You know, and then you're under. I don't want that shit. "What's the chance going to rain, snow tomorrow?" 50%. What? How do I plan anything? Right? Yeah. But his thought process, and I'm not shitting on him because he's a smart dude, but probability is just not inherent. It's not something that's built into us. Beyond basic probability, such as if I go this way, there's at this time that when the sun, let me say, if I this way, sun there, saber-toothed lion eat now, and they live here. So I'm going to go this way because there's a higher probability I'll live. That's the extent of what's built into us, because that's all we needed to survive and evolve. And if you don't believe in evolution, I don't know what to do with you. All right. All right. So the rest of it is not inherent. It doesn't make immediate sense. And here's a really good example. I don't think I did this yet. Did I do the Monty Python problem with you? Not Monty Python. Monty Hall problem. Oh, Monty Python. Anybody know Monty Python?
Yeah.
Okay. The one about the doors and the prize. Did I do that one yet?
No.
Okay. You guys know the Let's Make a Deal show? Have you ever heard of it?
Yeah.
All right. So what it used to be, at the end of the show, because I think they changed it up, but at the end of the show there were 3 doors, and somebody who won could trade their winnings in and pick a door. Behind 2 of these doors was a goat. Right? And we're assuming you're not trying to win a goat. We're assuming you don't want to get the goat. Everybody with me so far? And behind the 3rd door was like $25,000 or an all expenses paid trip to Aruba or something nice, right? A car. You with me? So obviously you want that door. What is somebody? So here's door 1, 2, 3. Somebody pick one.
1.
Okay. Right? So in my head, I've got a door with the prize behind it. Now, you with me? So I'm the host. I know where the prize is. Keep this in mind. What is the probability right now that she won? 1 out of 3. Is everybody cool with that? That's the basic idea of probability is it's the number of things that match what you want divided by the total number of things, right? And you know the basic probability. You do. It's just a ratio of what I just said. So there's 1 prize behind a door out of 3 doors. So what's the probability that the prize is behind 2 or 3?
2 or 3.
I want you to really, really keep these in mind. Now, I open door number 2, and I show you, let's make him green just so he's a little freaky looking mutant goat. I show you irradiated mutant goat. He's got a backward facing eye, I like it.
Wow.
Spider goat, spider goat. It's really fat. It's really been eating a lot behind the door. There used to be somebody back there, but oh. So I show you this. You with me? I open this door and I show you the goat there. And then I say to you, do you want to switch doors? Does it make a difference?
No.
Stop. See? Why did I open that door? So, stay with me now. Watch. 1 out of 3 times you will have picked the prize, correct? You with me? You got a 1/3 chance to actually pick the prize. If you don't pick a prize, 2/3 of the time you won't pick a prize, correct? Which means one of these doors has the prize and one of these doors has a goat. Now, which door would I not open because then the show is over?
2.
No. Come on. I love you guys. I want there to be drama. So I want you to have to make a choice. If I open the door with the prize, show's over. Where's the drama? You with me?
Yeah.
So is there a reason I might have opened this door? Because 2/3 of the time, what would be back here? The prize. So you should switch. Now watch. People have trouble with this because there's only 3 doors. And the mistake people make is they say, well, now there's 2 doors. It's a 50% chance. Probabilities can't do that shit. There's a 1/3 chance you won. So there's a 2/3 chance you won't win unless you switch. There is a 2/3 chance the prize is here. Now watch, let me show you. Here's where it gets a little bit easier. Ready? Wait, stop, stay with me. Let me take this to the extreme. What if there were 100 doors? We're in a big ass studio. You with me? So there's 100 doors. Somebody pick a number from 1 to 100.
45?
45. Whoa. All right. So you here's the 45th door. What's the probability you won right now already? 1 out of 100. I then, all right, you pick this one. This is your pick. I open every other freaking door except 3. Why didn't I open the 3rd one? Because I bet you anything, the freaking prize is there. You see what I'm saying?
Yeah.
Anytime you pick, when I open the other doors, if you didn't pick the prize, the one I leave not opened will have the prize.
Oh.
How many times will that door not have the prize? All right, let me try to say this again. There's only a 1 out of 100 chance you pick the prize.
Okay. Yeah.
So there's only a 1 out of 100 chance that has a goat. So there's 99 times the chance to win if you switch doors. Does that mean you definitely will win if you switch? No. But does it mean you should switch? Yeah. You increase your chances, don't you? Have you ever heard of the show Mythbusters?
Yeah.
They did a whole show about this shit. They set up a whole experiment. They had people come in, and they verified that the probability of winning was about twice as much if you switched doors. So this is the last thing I'll say. So let's say you pick the goat, which has got a 2/3 chance you pick a goat, right?
Mm-hmm.
So 2 out of 3 times, the prize will be here behind the door I don't pick to open. That's why it's better to switch. There's a 2/3 chance the door I didn't open because the prize is there. Okay, maybe. Now, even now, some of you guys are like, holy shit. I don't do this to show you the kind of problem you're going to have to work out. You're not going to have to work out this kind of problem. You with me? I do this to show you that probability is not inherent. It doesn't make immediate sense to us besides what helped us survive, because that's all that evolution gave a shit about. Right? Okay, maybe. Does that one make more sense, though? This one's normally more in people's face. If there's one door I didn't open, it's got to have the freaking prize. Are you kidding me? There's only a 1 out of 100 chance I picked it, so there's a much higher chance the door you didn't open has the prize behind it. Okay, enough of that. Okay. That's called the money hall problem. So the thing there is, as the host, I have information. So when I open a door, I'm using my knowledge. So it's not 50-50 because I knew something. Okay, all right, enough of that. So let's get into something we'll actually have to worry about. We're going to do kind of a lot today. Remember now, also, on your homework sheet, you should see there's a double quiz on this chapter. I used to call it a mini test, and people freaked out. It's a double quiz because it's twice as long and it counts twice as much. Crazy. So that's why it's a double quiz. Just on probability. So one kind of problem I love to give is this one. Let's see. All right. So I ask a group of men and women a question. And then here's their answers. Yes, no, maybe, right? So the question could be whatever's in your, are you going to vote in the next election? Let's say that's the question. Are you with me? How many of you guys are going to vote in the next election, by the way? Holy shit.
Yeah.
So, some of you, how many people just don't like to raise their hand for anything? Oh, that's funny. Somebody actually raised their hand. Quick note.
We
I'm not going to say you should vote a certain way or another. You should just vote, unless you're not old enough. That I understand. But if you are old enough, you should vote. Right? You have to. And I'm not saying to vote one way or the other. I don't care. We just need more people to vote. That's the only way that this is going to work. I'm sorry. That's enough. That's enough. I'll stop. I'm kind of a big politics kind of person. I'll stop. Okay. So, let's say these are the responses I get. Alright. Just to make up some stuff. So, around the edges here, I can do some stuff. How many total people said yes? How many total people said yes?
83.
Yeah, 83, right?
Yeah.
83 people said yes. How many said no?
28.
How many said maybe?
8.
Is everybody cool with all that?
Mm-hmm.
Nothing amazing there. How many men were there in this study? 3 and 17 is 20.
20
Plus 45 is 65. How many women were there? How many women were there? 54. Yes, yes?
Mm-hmm.
Now, one big mistake I see people make when we do this is they'll put down here 238, which is counting everybody twice. How many people were there?
83. Wait, no, hold on.
How many people were there? 65 men, 54 women.
Oh.
So if you add this way, it should come out to be, we can do it. Are these different people than these? No. So these should add it to be 119, of course. Is everybody with me?
Mm-hmm.
Just don't do 119 plus 119 and make people. Yes, humans can make people, but not like that. Right? You with me?
Yeah.
Don't count everybody twice. It's a nice check, though. This is 119, and thank God, this is 119. So there are 119 total people I talked to. Is that cool?
Yeah.
So this is called a, I don't care too much about names normally, but this is called a contingency table, in case you see that somewhere. The amount of yeses is contingent on the gender, right? Okay. And yes, I'm aware that this kind of problem, it's just easy to say men and women. I am aware I could have another category for other designations, right? Okay. But just to make it quick and easy to do probability problems, this is nice. If I pick one person at random from this group, what's the probability that I pick a woman? See if you guys get the idea of what we said earlier.
1 out of 119.
All right, now, did I say what's the probability that I pick my neighbor Fran?
Oh, no.
No. The answer would have been 1 out of 119 if I said, what's the probability that I pick Fran, my next door neighbor? That would have been 1 person out of 19. I want I want a woman. I want to pick a woman. How many chances are there for that? 54 out of 119. And I know a lot of you guys said that. I appreciate that. 69 out of 20, it's like 45% almost. Is that right? No, yeah, sounds about right. 0.45, maybe? Something close?
Yes.
What is it?
45.3%.
0.45. Go up, 2 more. 37.
Yeah.
And what's the next number after that?
8.
So really, what do you mean?
8.
There you go. So probabilities, we will take out to 4 decimal places. Standard deviations have to be at least 3. So you can make them 4 if you want to, and then just make everything 4. Do you see how that works? No? All right. If you make this into a percentage, I think somebody already did, what would it look like? 47.3%. I like it. Is everybody with me so far? I mean, that's the basic idea. The biggest mistake is when I get people say one out of something, one out of something. That is way too specific. I didn't say a particular woman, right? I said any woman. So what's the probability I pick somebody who said maybe?
8 out of
Yeah, how many chances are there? 8 chances to get somebody to say maybe. Out of how many total people?
119.
119. In fact, the bottom will always be 119 unless we knew something about the person. So we're going to get to that. So what do you guys think about this? What's the probability I pick a man or somebody who said yes? Careful, a man
60.
or somebody who said yes. I want a single answer because that's one probability question. It needs one probability answer.
Would be 45. Would it be over 119?
110.
65, right? Because we're doing all men and yes.
It says men or they said yes. So how many men are there?
65.
So if I do this, what have I done wrong? 65 men. How many people said yes?
83.
83.
But the 65.
What have I done wrong?
That is 45.
Do you understand that basic idea? So watch this, watch this. Here's the idea. We're about to do an and problem.
Yeah.
In math. Or is the nice bouncer. Or is the bouncer that says, I come up to the bouncer and he says, all right, to get in this club, you got to make a lot of money. I'm a teacher. Oh, shit. All right, you got to dress nice. Shit. Or you got to know Joe. I know Joe. Hey, Joe. Hey, Joe. And then I go in. You with me? That's the nice bouncer. Or is the nice way, because do you have to meet every requirement, Jeff? I killed a little buddy. All right. Do you have to meet every requirement to get in the bar if it's or? No, I just have to meet one of them, right?
Yeah.
So I have more chances to get into the bar. So the probability of me getting in gets bigger.
Mm-hmm.
What if the bartender said this? All right, to get in the bar, you got to know Joe. I know Joe. Hey, Joe. And you got to make a lot of money. I'll stop right there. I'm done. You guys with me?
Yeah.
Have any of you guys ever applied for a scholarship?
Yes.
And when you look through the scholarship requirements, it's all ands.
Yeah.
I love it. This is a true story. Back in my day, before the internet's really caught on, there was this book about this big in the financial aid office of all these scholarships. And it was such an amazing waste of paper because they updated it like every 3 weeks or something insane. So they throw that one out and a new one would come in. So you go in there and you go, okay, all right, you must be a math major. You must have this GPA. Barely. You must do this, you must do this, and you must do this. And you must be a woman. Ah, shit. I mean, that actually happened to me. I'm like, put that first. Holy shit. You guys good with me? Mm-hmm. And so you turn the page, and then you got another one. So you got it for and, it's going to always decrease the probability because you have to meet all the requirements. You with me? Or makes everything more. But what's the problem then? I include all the men, I include all the people that said yes.
But then you're including women there, and it's asking.
No.
No,
Did I
it's
say
not.
it couldn't be a woman? Does it say anywhere there that it can't be a woman?
Okay.
It could be a dude or somebody who said yes.
Okay.
You're including men twice.
I'm including some people twice. Do you guys see that?
Yeah.
Which people did I include twice?
45
People
men
say
plus-
yes.
Those people I included
Yeah.
twice. How the shit do I do that? Right? I clone those dudes. Do you guys see what I'm saying?
Yeah.
So, or seems to mean add, except I have to adjust it if there's any that match both.
Then it would be 38.
So watch. So what do I have to subtract off of here?
45.
45, because there's 45 people that match both. I can only count people once. Do you guys see that? And that'll be out of how many? Yes, because that's the total possibilities that could happen. Now you could have been smart and said 65 men plus 38 that I haven't counted yet, right? If anybody was thinking that, that's beautiful. Because what is 83 minus 45?
103.
38, right? So you could have just said 65 men plus 38 yes people I haven't counted yet. You guys see what I'm saying? And then whatever the hell this is. Whatever the hell that is.
0.8655.
8655?
Yeah.
Yeah, okay. Bless you. There we go, Jeff. Sorry if you're playing along at home. Now you can see everything. Or 86.55%. So right now, let's develop our first real official formula for probability. Have we done a lot of probability questions? Or a decent amount, right? Have we done, we've done 3 probability questions. Have I given you any formulas yet?
No.
So I want you to realize, this is a very strange thing to hear from a math person. Formulas have to include everything that could happen. So they are very often more complicated than a specific situation needs. So if I'm given everything I need to count, I actually don't need the probability formulas at all. I didn't need a formula to do that. I just needed the idea of how many matches we're looking for divided by the total, right? But here's what the formula looks like for or. The probability of something or something else. What is this? That's the probability of a man. So the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. So or basically means at. Basically is there because I have to adjust it if I counted anybody twice. Okay. So what the shit is and? All right, let's see. Let's try an and problem. Where'd it go? Oh, there's a blue one. Does that work? Almost. No. Okay. Man. Gotta give me some. Oh, wait. See if you work. Oh, yeah. All right. So let's try and. What's the probability that I pick a woman and she said no? Think about this.
It's gonna be 11 out of 119.
Say again?
11?
Yes.
Yeah.
How many women said no?
11.
11. You see that?
Yeah. And.
So watch this. And is very often called intersection. Watch. Here's the women. Here's the people that said no. Do you see the intersection?
Yeah.
Yeah. That's why and very often is called an intersection. They have to have done both. What did I say earlier? The and bouncer will always decrease your chances. It's always going to make the probability less because you have to meet all the requirements. You with me? A little bit? So probably woman and no is 11 out of what?
119.
Yes, it still could be anybody. Yes, Jeff. What the hell was that? I'm trying to do that in my head. Screw it. What is that? It's 111, so it's like 09.
24.
Okay. Or 9.24%. Is that cool? Okay. I like it. So we haven't seen a problem yet where the bottom changes. So let's try one of those.
Yeah.
Take this one away. Well, do I want to take that one? Sure, I'll take that one. So let's see. E. What's the probability that I pick somebody who said yes, given that they're a man? So let me say that again. What's the probability that I get somebody who said yes, given that they're a dude?
45.
It's greater than 1. That doesn't make sense. Gotta be careful.
What is
So, how many people could it be?
That said yes.
All right, let me try again.
Out of the
The
whole.
probability that the person said yes, given that they're a dude.
Oh.
What kind of person is it?
Someone.
What do I know about this person?
You're saying yes.
No, let me try again. What's the probability they said yes?
Given that they're.
I don't know if they said yes.
They're
Given they're a dude. So what do I know about the person?
man.
They're a dude. They're a man.
Mhm.
So how many people could it be?
465.
So out of the 65, so I'm given that it's a man. So the given part changes the denominator. Who have I thrown out? I threw out all the women. So get out of here, right? And they're like,
So it'd be 44.
for my future evaluations. Jeff,
So 45
Because it said
out of
yes, right?
65.
now be careful. So yeah, 45.
Yes.
I like it. So your universe becomes that. That's a good way to do these problems. For a given problem, you know it's a man. So there's your whole universe. So 45 said yes out of 65. Nine out of 13. Oh shit.
Points. 6923.
6923.
Yeah. 69.23%.
All right. So you guys try this one. What's the probability that they are a woman, given that they said maybe?
Five out of.
So what's your world now? What is the bottom going to be? What's the bottom going to be?
84.
What am I given? I'm given they said maybe.
8.
Oh,
So I
okay.
know that about the person. So I'm only talking about 8 people then, right?
8.
Given that they said maybe, so out of 8 people, how many match what I'm looking for?
Oh, 54.
5.
5. Oh.
In fact, if you do this, how do you know you are wrong immediately? What's the biggest the probability can be?
100.
1 or
Yes.
100%.
Yeah.
And that's going to
That
be
would
way over
Yeah.
1,
Okay.
right?
Yeah.
So, given they said maybe, there's my whole universe. That's the only people that exist now. How many are women? 5. And that one's a nice one, right? That's 0.625. 62.5%. Become a 5. You guys with me? A little bit? So givens are the only time the bottom changes. Because then I'm throwing people out. I'm given as this kind of person, so I can throw everybody else out. So when you do the problem, you can actually just cover everybody else over. They're not here anymore. Yes?
So whatever comes after given is gonna
On the
go
bottom.
to the bottom.
Yeah.
Okay.
So let's actually see what the hell this formula is. We've got enough examples to see what this formula is. I'm going to leave that one up there for a minute. All right, let's see if we can piece this together. By the way, here's the symbol for given. This means probability of A given B. That's a straight up and down line. That is the symbol for it, right? That's not what I chose, it just is what it is. That doesn't mean divide, it means given. So what is this formula going to be? Well, what's the bottom come from? Like you just said.
Part after.
The bottom comes from the given part, right? So the probability of A given B, on the bottom is going to be the probability of the B, right? Now what's the only way you could get on the top? So up top, did I put all the women? No, I didn't. They had to do what? They had to be the women who said maybe. So it had to be women and maybe. So the only way to get on the top now is if you're A and B. That was the formula that we just used without even knowing that was the formula. Maybe? Maybe? Is it just me? me or is it warm in here? It's probably just me. Okay. So I don't remember. Oh yeah, okay. So watch this. Let's do one more of these. What time is it? Ooh, we got so much time. You guys hate that. Too bad. What's the probability that somebody said maybe given that they're a man? Take a minute and do that one. So what do you guys get? What's the probability somebody said maybe given that they're a dude?
3 out of 60.
Yeah, good. It's gonna be 65 for the dudes, and 3 of those are
Maybe.
said maybe. Yeah, thank you. And what is that? 3 divided by 65.
0.461.
All right, I like it. Now watch this. Watch this. See if you guys. This is a really freaky part. What was the probability somebody just said maybe? Why didn't we do this? 8 out of 119, right? We did this one earlier.
Yeah.
What is 8 divided by 119?
It was 0.0672.
0.0672?
Mhm.
Stay with me now. Stay with me now. This is the part that drives me a little insane. It really is actually straightforward, but for some reason nobody ever believes me. Did the probability that somebody says maybe, did it change if I knew they were a dude?
Yeah.
Yes.
Went down.
What was it before? It's probably somebody just says maybe. 6.72%. If I know they're a dude, did the probability they say maybe change?
Yes.
Yeah, it went
Down.
down a little bit, right? Knowing they're a dude changed the probability they said maybe. Right? So it seems that the occurrence of man changes the probability of what they said maybe, whatever. You with me? Yes? So would you call those two events, what I just said, does it make sense to call them dependent or does it make sense to call them independent?
Dependent?
Dependent, of course. What's the probability they said maybe? Well, it depends on if they're a dude or not, right? Doesn't it change?
Yeah.
Let's try this one. What's the probability they said maybe given they're a woman? That's what that is.
5 out of 54.
Yeah, 5 out of 54, which is, that's going to be 09 something again.
0926.
Or 9.26%. So watch this. Not having any information about what kind of person they are, man or woman, it's 6.72%. What is the real probability they said maybe? It depends on if they're a man or woman, because it goes down for men and it goes up for women, doesn't it? You guys see that?
Yeah.
So it makes sense then to call those events dependent. Doesn't the probability of something happening, of maybe happening, depend on if they're a man or a woman? The mistake students make is they hear the word depend and they say something like, they could say maybe if they're not a man, or they could say maybe, they don't have to be a man to say maybe. They're not dependent. No. The probabilities are the probabilities dependent. Yes, probability changes. So the idea of independence is thus. Here we go. Take all this stuff. Independent events. The test for independent events. If the probability of A given B is the same as what the probability of A used to be, then they are truly independent. They don't give a shit about each other. Hey, be happy. I don't care. That would be independent. If it changes like it did here, right? If it changes like it did there, then they are dependent. It doesn't mean that one can't happen without the other one. That's not what I just said. Do the probabilities change? So let me give you an example I got in trouble for it. I just keep doing it anyway, because it was really exciting when I got in trouble for it. And you guys are like, what the hell is he going to say? So let's say off in the distance, way far away, you see somebody, they're so far away, you can't even tell if they're a man or woman. You with me? Right? And you're like, we'll find out. So right now it's like a 50-50 shot. They're a man or woman. You with me? Roughly. What if you noticed that they just got off a Harley Davidson motorcycle? Are the probabilities the same still?
They are. They
I love you guys so much. See, this is where some people get upset at what they think I'm trying to say. Who rides Harley Davidson motorcycles more, men or women? Men. Did I just say that no women ride Harley Davidson motorcycles? No. I try to make this example because people have their emotions come into things that are just numbers. They're not saying what it sounds like I'm trying to say. So if I saw somebody get off a Harley Davidson motorcycle, is the probability they're a dude, did it go up?
Yeah.
Shit, yes. Does that mean they're a dude?
No.
I don't know yet. But I feel pretty good that they're probably a guy. If it is a woman, I'll go, okay, wow. Right?
Yeah.
All right, maybe. That door back there, I don't know about this example. I was going to say something about, well, it's probably somebody's going to have to duck. Well, it's depending on how tall they are, right? But oh, that's not about that. Does that kind of make sense? It's just, does the occurrence of something change the probability of something else? That is dependent if they do. Doesn't mean it goes to nothing. It just means it changes. Okay, I love it. I remember this one semester, some woman in the front seat was just really upset at me. She was like, I'm waiting for some teacher to say something chauvinistic, and I think you just did. I'm going to unleash on you. I'm like, that's not the point of this at all. In fact, that's why I like that example, because you got to realize what it really is saying. Right? Okay, maybe. Okay, bye-bye. One more thing, and then I'm going to give you this worksheet so I can shut up and not get in any more trouble. At least for a little. Yeah, let's do this. Where'd you go? I used to have a black pen. Oh, too bad for you, Jeff. All right, so everybody's got this here?
Yeah.
This seems to be important. So we have this formula. Let me write down the formulas we've got so far. We got this formula. What formula are we missing?
The or.
And?
Wait, no.
And.
Yeah.
Now, mathematically, we could actually make one right now. Before I do, I want to make sure you see why it makes sense. You guys remember, it's terrible I have to say it like this, but you guys know that the space shuttle blew up several times now, right? Not the same one, obviously, but back in '86, I lived down in Florida. We used to go out and watch the shuttle take off. And I was like a major geek about the space shuttle. Holy shit. So this one time, for some reason, we didn't go out. Maybe it was too cloudy. I can't remember exactly what it was. I still remember I was in English class, sitting against the wall, because the door's right there, right? And I still remember when I came over the loudspeaker, the announcement stuff that said, just to let you know, the space shuttle just blew up. It seems that, I don't know how they said it. I just was like, ball. And for some reason, we didn't go out to see it. I think it might have been because it was too cloudy. All right, you guys all are aware of this fact, right? And then, of course, the space shuttle blew up again because it came back into orbit and its heat tiles had suffered a lot of damage. And so it blew up over Texas and whatever. You guys know about that one, too. You guys with me? Okay. Now, that first time in '86, you guys, does anyone know why it blew up? Okay.
Not exactly.
Not exactly. All right. So here's why it blew up. There was a fuel line, and then the fuel line, there's these things called O-rings. Basically, the O-rings were like valves to make sure the gas didn't go the wrong way, or else what happened would happen. Does that make sense so far? Right? If the gas is going the wrong way through, it's probably bad, right? So, these normally have a very small chance of failing. Even with that, why do you think they had multiple of them?
Because one can stop the gas.
Yeah, if you live in a really bad neighborhood, what do you have multiple of on your door?
Locks.
Locks. And in fact, are they all the same kind of lock? No. So you're like, if you're getting in, you gotta really know your shit. So
Yeah.
I'll pick this one, but can you pick this one? Yes. Oh shit, can you pick this one? You guys with me? And yes, I used to live in a neighborhood where I needed 3 different locks, another door with its own locks. So I understand, right? It was cheap though. It was, and I survived. Yay. All right. Why do you do that? Why would you have multiple locks? Because the more locks you put in,
The harder.
the less chance it is they'll get in.
Yeah.
What if you really got to take this final exam? It's really early, like ours will be. So you want to make sure you wake up. What are you going to set? You're going to set
every
multiple
day.
alarms, right?
Yeah.
You're going to set your phone alarm, your little alarm clock. You're going to call a friend and say, "Can you call me at like 6:30?" And it's like, no,
No.
right? But you have multiple things. Why? Because each one could possibly fail. So you have backups.
Yeah.
So I can't add these probabilities like I do with OR, right? The probability of this or this or this, I add them, don't I? Because let's just say that the probability that one of these fails is 0.01, 1% chance. Are you with me? Each one. So if the total probability that all of these failed was 3%, why would I put multiple? Why would I do it if they added? So they obviously can't add, or else there'd be no point to do multiple things. All right, so here's how this works. What percent of the time does this fail? 1%. So 1% of the time that one fails. Of those times, what percent will this one fail? 1%. Of 1%. And what percent will this one fail?
1%.
1%. Of 1% of 1%. 0.01 times 0.01 times 0.01.
So like.
Right? Holy shit. So it's a 1 with 1, 2, 3, 4, 5, 6. With me?
Yeah.
That makes more sense. You want the addition of these extra things to reduce the chance, in this case, of explosion, or to increase the chance that you wake up, right? To decrease the chance that none of the clocks go off or that you don't wake up. Are you guys with me? So, and seems to mean what operation? Multiply.
Oh.
Yes?
Would it also be like raising it to a power, or is that?
Sure. This is like 0.01 to the third, which matches up with there being 3 O-rings.
Like,
so if there were 8 O-rings, it would be 0.01 to the eighth
Okay.
power, kick-ass. Right, because that's what exponents are for, so you don't have to write 0.018 times. You guys with me, everybody?
Yeah.
Some of you guys? Some of you guys are watching shows or sleeping, but most of you guys are looking at me. Okay. So that's the serious example. Here's the silly example. So I apologize, but I like this. Let's say you're about to join a fraternity or a sorority, right? Maybe it's Sigma, 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 right? And they do some very, very light hazing. Nothing is going to get them in the news. Nothing is going to kill anybody. What they do is, I've got to walk down this hallway, and every third step I take, somebody slaps me on that cheek. Right? And every fifth step I take, somebody slaps me on that cheek. Are you with me? You understand? So what percentage of the time? 1/3 of the time here, right? 1/5 of the time here. So how often will I get hit on this cheek and this cheek? You can do it. Every 3 steps here, every 5 steps here.
8 steps?
How often? No. No. Nope, that doesn't make sense because 8 is not a multiple of 5. Do you see? You could do it.